Hello, friends. I'm Paige Heller. I'm the CEO of Endpoint Security, a startup company in cyberspace. I'd like to talk to you today about something that's not rocket science. In fact, it's very applied. It's an applied science uh, to a very specific topic. So today I'd like to take a very practical look at using wireless frequency domain data and its manipulation for embedded systems using cybersecurity applications. My background is actually not in uh, cybersecurity. My background has been in um, industrial control design. So I got involved in cybersecurity about 4 years ago, and during that time, I've learned a lot about the area and specifically about its application in industrial control systems. So I have taken that and created a specific interest in using polarization of wireless signals as a sort of fingerprint for the wireless signal. So I can tell what device is sending the signal simply by its natural fingerprint embedded in a radio frequency signal. So I would say that probably our expertise in the company centers around RF signal polarization characterization, and specifically for applications of cybersecurity in industrial control systems. That's a pretty narrow area. So I hope you find something enjoyable or at least interesting in the presentation. We're always looking for people with expertise in 3D curve matching because the data that we get, the fingerprint that we derive from an RF signal is a 3D signal, as you can see on the right of this slide right behind me. And we're always interested in machine learning applications for real-time systems. The challenge that we're going to talk about today is the fact that industry is beginning to adopt wireless sensors pretty rapidly. And it makes perfect sense because the wireless sensors and actuators are easy to install. So if you already have a plant in existence, it's easier to put in something that's wireless than wired. But of course, the difficulty is that wireless devices always add a particular entry point into the network for an attacker. So particularly those that are older systems that have been installed for a while create a new attack vector that you don't want in your plant. So we took a look at how to try to solve this problem. It's not easy because wireless devices, it's not even easy to detect an attack because the attack is usually that someone imitates the wireless device and it looks perfectly natural to the network to be communicating with them. But there's about 30 million wireless industrial devices installed today. And if you think of it, a lot of those are perhaps 5 to 10 years old, and they don't have the current methods of cybersecurity. So those all represent the weakest point in a particular factory and therefore are very interesting to attackers as an entry point. So we want to try to close off that entry point. And we came up with a method to, along with the University of Notre Dame, to recognize a fingerprint in radio frequency signals. And with that naturally occurring fingerprint, we can decide whether the device has been authenticated and is allowed to talk to the network or whether we should block it. We originally thought we were going to design a new chipset in order to do this, but it turns out that industrial routers and gateways have plenty of electronics to handle what we're doing. So we won't even have to do that. We will simply license the technology to access point manufacturers. So I'm going to talk to you today about a very specific angle of this kind of technology, because it might be useful in other applications where people are dealing with the frequency domain data of wireless signals. So an access point sees this kind of information arriving at its receiving antenna. This is a time domain plot of signals that are arriving. You can see it's done by samples on the horizontal axis, and we're sitting around the 7 million sample mark and looking at these signals. But you see quite a variety of different kinds of signals. You can tell that they're different from one another. And we can derive a little bit of information from this, but probably not enough to actually identify a device. For instance, we can tell that the first signal, it's longer than the rest. So it is probably a device that's connected to the access point and sending data. We see one that looks similar to it, but is much more narrow to the right, which is probably the same access point sending a beacon out to introduce itself to other devices that may want to connect. And we see some that are very, very narrow. There's two side by side right in the center that are probably Bluetooth signals. They're probably not even Wi-Fi or Zigbee. And then finally, just to my left is a very low signal to noise ratio signal that's fairly wide. It looks kind of like the wider signal, so it's probably something that's communicating with another access point somewhere else, and we're picking it up. But this information is not enough, of course, to say what these devices are. Can you say that the two that are wider are exactly the same device? Maybe there are two different devices in the plant communicating with the access point, and so forth and so on. So the time domain data is just not a good place to go to find this kind of information. So we look at the frequency domain data instead, and in particular, we use polarization. So let's review polarization just a little bit. It's not something that's common in the cybersecurity world. So what actually happens when a device sends a polarized signal is that it may be a temperature sensor, for instance, that has an antenna that sends a vertically polarized signal. That would be one example. And when it does, that signal is traveling in a vertical plane. So it's sending sinusoidal data in a vertical plane to the access point. But of course, it doesn't go straight. It bounces off of walls, it bounces off of the ceiling. The multipath channel from the transmitting device to the receiver is quite large. So it bounces off of equipment, people, in any number of things on its way to the receiver. And when it does, each time it hits something that has a little bit different dielectric constant, it actually twists the polarization. So the polarization changes every time the signal bounces off of something. Now, this is usually detrimental because it ends up spreading the signal at the receiver, which is something that's undesirable. But we have to live with it. So we figure out ways to detect the data in this received signal that is spread somewhat. But for our application, it actually contains information. And it turns out it's quite stable, which is very interesting. So we use that to derive a fingerprint. And to do that, we have to move to the frequency domain. You know, the nice thing about recording these presentations is I could talk for hours about this, and you would just have to sit and listen. But I'm not going to do that. So we move to the frequency domain in order to derive polarization. So here's where the problem that I'm going to address today comes in. When we go to the frequency domain, we often do that with a digital Fourier transform, DFT, a digital Fourier transform. And when we do a transform, we begin with the assumption that the period of time, the number of samples we're going to use to do the transform is an ideal exact number that represents one full cycle of a signal of interest, like the chart in the upper left. However, we don't have a single frequency of interest. We have a bandwidth, and there are many frequencies in a wireless signal sent from a transmitter to a receiver. So what happens is we get many frequencies that aren't a full cycle. They're either more than a full cycle or less than a full cycle. And when that happens, we get a discontinuity, like the lower left in the chart on the left. So the result of that discontinuity in the mathematics yields what we call side lobes. That's what you see around the center. There's a large center lobe, which we call the main lobe, and then smaller and smaller side lobes out to each side of it. Those are the results of the math, not the frequency contained in the data itself. Here's what a real example looks like. So this was recorded by our prototype. It's a Wi-Fi signal, and you can see that there is a main lobe in the center, and then there are what we call side lobes. And in this case, there's probably 3 side lobes that we can see here. Well, since those are artifacts of the math, we really don't want those in our calculation. Not only that, they take up space. So in a real-time application, you're really concerned about database space, and you'd rather have the information that is most valuable stored without storing anything extra. So we really need a way to identify that main lobe. So if we start at 0 and we work our way across, how would we choose a threshold that wouldn't catch one of the side lobes as being part of the main lobe? It would be difficult at best. So perhaps an easier, and by easier I mean less code, so it's lighter weight in the final application, takes less time to compute. It would be nice if we could find a point that's somewhere in that main lobe and use a threshold forwards and backwards to find those edges. So that's what we do. We select a point, and I'm going to begin by suggesting, let's just take the top two peaks, because there isn't a peak in the center. It actually dips, right? So we'll just take the top two highest points and select a point that's halfway in between. I call this the center, and you'll hear me mention the center point. It's not exactly the center of the FFT or the DFT, but it is somewhere in the main lobe. And that's all we really need to do, is get somewhere in the main lobe. So it is actually the center of the highest 2 points. Now, if we do that, then we can march forwards and backwards to find those dotted lines, which is our goal, is to find those dotted lines that mark the edges of the main lobe. So that's the goal we're setting out to do. Now, there is an interesting aspect of this that I haven't mentioned. The chart that I show you looks nice and solid, but in fact it's not. It's just the width of those lines that are drawn on the chart that make it look solid. If you expand a small section of it, as I have in the arrow on the left, you can actually see that there are many, many samples that are actually close to zero. And so we can't just look for a sample that's close to zero as our threshold. So instead, we must do some sort of averaging. So I show you in orange the average of these, and you see that it's much lower. The reason it's much lower, of course, is because many of those samples are actually close to zero. So we're going to use the orange, except why, if we're interested in doing less computing, why would we use the average where we have to do a division? So rather than using the average, which I'm showing here, we'll use a summation, a moving summation going forwards and backwards from the center point. So we pick a center point somewhere in the main lobe, and we'll march forwards and backwards from that point using the summation data. That'll carry the same shape as that orange line, but it'll be much larger, of course, based on the summation window. Now, what do we use as a threshold? Well, we only have to calculate the threshold once for each type of device, so we can be a little bit more liberal here. And in this particular case, I have chosen a method of sorting the DFT data that you saw in the previous chart from low to high. And this is what the sorted data looks like. There's a considerable amount in the left-hand half of this data that's closer to zero. So I just choose a value in the center of the first quartile and then use a multiplier. So I assume that the data in the center of the first quartile is close to the noise floor. And then I'm going to move above the noise floor at some level by multiplying that value by a factor. In my case, the summation window is 20 samples. So if I choose a multiplier of 20, it will be exactly the noise floor, since I'm doing a summation rather than an average. So probably a realistic value would be more like 40, which would be 2 times the noise floor. So you can see that threshold just in the white right here. That threshold for this particular case happens to be right as I draw this white line. So we're going to apply that. That's adjusted for this average curve, of course. So this is where we're going to demark where that dotted line should be. And it's very simple to do that way. So we can actually get pretty close. It's not exact, but it's pretty close to the edge of the main lobe, and it uses very little code and very little computation time. So that's the secret, is to make sure that it's always low computation time. So we applied this to our data. We have many terabytes of data that we've gathered over many different situations. And we noticed that when the signal to noise ratio is quite low, we often get a sample, a single sample that probably is a result of the noise floor, the frequencies in the noise floor uh, summed in the DFT process, which actually becomes significant when the true signal is very low. So it ends up with a single point in number 5 on the far left and in number 8 in the far right that is higher than the main lobe. So we had to take into account that, and we don't use the 2 highest peaks any longer. We use the second highest and third highest to find our center point. So that's an area to watch out for. Very low signal to noise ratio signals are always a problem because they're more unpredictable. So in this case, for instance, you might see that the second and third highest signals aren't in the center of the main lobe at all. They're off to the side. That's okay, because we're going to increment from that point forwards and backwards, but it does present an interesting problem. Notice that this signal to noise, this signal, I should say, the center of the signal is very close to 0. That's due to the Barker code that's used in the short and long training sequences. So it's something that we have to be concerned with, because we don't want to just capture half of the main lobe. We'd really like the full main lobe. So there's 2 ways around this. One is by increasing the summation window size, which we have done. And the other is, even if it is centered, you're in that awkward area where you're probably got something that's close to 0. So we create a margin, and you see that margin above the bracket showing the 2 highest peaks. There's a margin in which we don't do the summation. We will start on either side of that. And when it's in the center, that works pretty well. But in this particular case, it's off to the right. And the way we had to address that was by increasing the summation window. There's also cases where the signal is not centered. In other words, the receiver is tuned to one channel, and the signal that's received is actually transmitted on a different channel, but within the bandwidth of the receiver. When that happens, you get something that looks like this, where this is probably just half of the main lobe. So in this particular case, we have to give up. We don't even see the other half of the main lobe. So we will have to just take half of the main lobe. The algorithm works fine in doing so, but you will have to take into account the boundaries. So when you hit 0, even if the signal is not below the threshold, you must use 0 as the starting point. That's pretty easy to do in code. And so what we end up with is a very simple concept of capturing the main lobe data and storing just the amount of data that we need in an embedded database, and using very low computation time. So as I said in the beginning, it's not rocket science. It's very applied, but I hope that it will enlighten someone who's working with radio frequency to actually think about some of the oddities that they might run into when they hit signals that are not on the right channel or have very low signal to noise ratio. I'd like to extend a special thanks to Stan McLellan for introducing me to this conference, and to Dr. Tom Pratt at the University of Notre Dame, who actually came up with the fundamental science behind the fingerprinting. If you're interested in the fingerprinting application, I am also doing a tutorial, which is a little bit more in depth and a higher, more broader, I should say, discussion of using polarization to derive a fingerprint from a wireless signal. So I hope you've enjoyed this. I hope you enjoy the rest of the conference as well. And thank you for attending. If you have any questions, please let me know. I'll be glad if you would just email me. I'll be glad to address anything that you might have. Thanks for your time, and enjoy the rest of the conference.